Just a few words about Secure Thingz. As Steve said, myself and Hayden, who's sitting over there, we've had a long background in IP development, IP deployment at our time with ARM. Now we're focusing around security issues, specifically around the IoT space. And how do you deliver secure platforms in the IoT at device end and the gateway end? And obviously, we have close partnership with some of the big IP players there. We've got a couple of strands of the things we're doing. One is secure thinking, which is our consultancy services. An example of that is we've worked with Renesas on their Synergy microcontroller platform in terms of security aspects of that. So we do things like threat analysis and system definition and architecture as well. And we also have a product-based thing called Secure Deploy, which is around controlling manufacture, being able to deliver material into devices during the manufacturing process. I'll talk a little bit about that later as a different type of example of IoT security. So we've heard all the presentations this morning, so I can skip this pretty quickly. Internet of Things, a slow-motion train wreck. How do we cope with that? What are the things that we can do? We can see it happening. How do we handle that from the whole life cycle of devices and systems, especially if you've got this multi-vendor type system or remote managed systems, and all the pieces you have to look at? We've talked about some of these earlier on today. So, handling confidentiality or handling enforcement, but how do you manage the whole life cycle? So we know that there are lots of people who understand the types of problems that we're going to see, but there's a whole mass of people who are going to build these 5 billion or 20 billion or however many units it's going to be, who probably don't understand what the issues are, or they understand a subset of the issues, or they understand maybe none of them. So it's all about, how do you deliver the best efforts to secure your application? But we've seen before, even with the best will in the world, designers are not infallible, and they never will be. As Tim said, we've got to presume that systems will be compromised. You can design it as well as you can up front, but as well as that, you have to be able to design systems so that for recovery, for update, and for remediation. And that is going to be a big mindset change for a lot of people. And produces a whole range of follow-on questions from that. So, when does an update need to be made? It might be obvious, it might not. Who takes responsibility for doing that update? Where in the value chain is that update managed from? Are there liability questions that need to be addressed? So, what are the system components that are impacted? Is it change the whole system from top to bottom? Is it just this piece changed here? What's the impact of that on some other part of the system over here? And as a user or someone else in the system, who do you trust to handle this or manage this process? We've had many more exciting talks this morning about IoT issues that people have raised about hacking, so I don't need to talk about that slide. But obviously, they have real impacts. And one of the things about attacks on IoT, they can be potentially attacking, real physical things. So an IT attack, might be claiming people's bank information or something like that. But things that are actually hacking physical devices can have much more immediate, life-threatening impacts on people. So we have to think very carefully about those types of problems. And in some ways, it's kind of a self-fulfilling prophecy, right? Because the more people talk about, well, it's the IoT, it's this big, it's huge, it starts becoming open season, lots of devices, and that just means huge security surface for attackers, lots of different types of system, lots of different vulnerabilities, potentially. There isn't going to be a one-size-fits-all security solution. But there can be guiding principles that you can apply to make them systems themselves more secure. Also, some types of cyber attacks are highly profitable. That drives some people. Other people are driven by just well, I can do it because it's fun, or someone said this is really hard to do, so therefore I'm going to do it. And the challenge for systems design is we need to aim to be secure 100% of the time. We're not going to be, but the flip side is attackers only need to be right once. You only need to find the right one vulnerability, and you broke into the system. And if the system's designed well, you've got multi-layers of defense, then that might allow you to do something, but they still only need to be right once, whereas you've got to have thought of all of the possible vulnerabilities and threats that might be there. So again, one of the reasons why IoT may be of benefit is because you can use it to generate big data, use big data in a sensible way to allow you to make savings potentially, or cost cutting, or do things more efficiently. And you get the flip side. If you have all this big data, you're making decisions based on what that data is telling you, then you need to be able to trust that data. You need to be able to understand that the data you're getting has some actual value for you. And it may be there's lots of tiny little pieces of data that you're getting from a whole dispersed range, but you need to be able to trust all of those so you can build up the big picture and make the right decisions. So, yeah, what is your strategy for IoT security? Cross your fingers behind your back. That seems to be the approach a lot of people take. You've got to get something to market. You've got to be out there. There's deadlines to meet. You've got to go get something there. So this is a list from the Council for Cybersecurity, which is talking about securing critical infrastructure and industry. And you can see a whole range of things here which are very applicable to the things we've been talking about today. I'm not going to go through them in detail, but you can see things like vulnerability assessments, being able to remediate, being able to update devices, securing configurations for network devices, having boundary defense, and maintaining data protection across your devices. So I was going to talk about the typical things you're talking about from a security perspective is handling confidentiality, handling integrity, and handling availability. But that can apply to a whole range of things in your system. So as I said, protecting intellectual property might be one thing. So the confidentiality of intellectual property in your system design might be something you want to protect. That's not a typical IT type security issue. But protecting data at rest or in flight, that's more kind of traditional like that. And how you do that from an integrity perspective, how do you keep the integrity of your system? How do you put robust foundations into the design that you're building? And how do you ensure that you have the right separation of functionality in a device? We saw earlier from the talk about Tesla, how they very carefully separated out the infotainment system from the rest of the car to provide an isolation mechanism. Right? So how do you handle that? They had a very good solution for providing availability in terms of being able to keep driving the car, even though the infotainment system was down. And overall, how do you manage the device life cycle for all the way from thinking about designing it, through designing it, building it, deploying it, and then also what do you do once you reach the end of the device's life? How do you remove it from the system? How do you ensure that any data that you have that is still confidential is no longer available? So one example of one of the things we've done is around, as I said, protection of critical intellectual property. So we've been working with microcontroller manufacturers and OEMs, where the OEM's saying, well, I want to manufacture 10,000 devices with my contract manufacturer out in the Far East. Okay, but if I just ship them the application binary, okay, how do I know there's not going to be another 10,000 grey market parts made at the end of the day? How do I know that device isn't going to be cloned, or someone's going to take the that software image and reapply it, or reverse engineer it? So we developed a mechanism which allows personalized devices, and the mechanism which would allow you to individually provide keys for an encrypted image to be downloaded onto the device, which can then be installed in situ on a per device basis, and allows the OEM then to have an understanding of the count of the number of devices that have been made, and the knowledge that the image has only been put on to devices that they've certified and built themselves. So I'll come back to the standard 3 pillars again around confidentiality, integrity, and availability. So in terms of things like low-end devices, we've seen that very tightly constrained devices in the past have typically had very low levels of specific security useful details in them. I think that's changing at the moment, and over the next couple of years that is going to change significantly. But there's definitely moves to do things like increase the protection available to data, being able to provide security across a portfolio of devices, including things like being able to provide accelerators for cryptography in devices, and that gives you a number of advantages I'll talk later. One of them is you can have a smaller code base, and these things can be very tightly integrated into the device and provide separate protection for secrets that you want to have, and protection against leakage mechanisms. If you want to have an integrity in device, you need to understand that as you come through the power-up mechanism, that you have some trust in what's actually running on the device. So putting an integrated root of trust on these types of devices can help you have assurance about the protection of the platform. So you can have a constrained measurable boot to make sure you can understand the state of the device as it powers up, and also mechanisms for the isolation of different pieces of code that you're running. So if you've got some critical code, either from a safety perspective or from a security perspective, you can isolate that from execution of code in the rest of the system to ensure that you've got some separation and resist the impact of a vulnerability that's been found. And then across the life cycle of devices, how do you use this isolation that you have in the critical system to promote uptime, or to promote mechanisms where the device can still be working part of the time or partially whilst an update mechanism is being used? What can you do to ensure that you've got ongoing monitoring and management of the functionality of the device as and when an attack happens, and going through to how do you ensure that you've got a management and update process which will enable you to recover from the type of attacks that might be. So talking about confidentiality in particular, there's a whole range of things that you might want to address. So confidentiality of data, so protecting business critical information, or it might be about providing privacy for a user so that data's personal information is not becoming available? Or how do you ensure there's non-repudiation in the system so that you can be able to do things like enforceable contracts? Typically, one of the methods of providing confidentiality through a communication mechanism on a device itself is using cryptographic methods. Cryptography itself doesn't equal security, and that's kind of a fundamental problem that we see when we talk to people who don't come from a security background at all. The first thing they think, well, I've got to put some crypto in, and well, yeah, crypto does a certain job. It's that one piece, but all that happens is someone goes around it from a million different directions. So, yeah, you might well want that. You may need that, but it's only the tip of the iceberg. If you've got cryptography, then the first question you have is, well, how do you manage the keys that you're using for that cryptography? How do you keep them confidential? How do you manage those? How do you provision them? What's their life cycle? So there's lots of standard ways of doing things, right? Don't reinvent the wheel. If you're doing some comms, utilize some existing standards. Use standard accelerators if they exist on your device. So crypto accelerators can usually reduce your power, which is probably something you may want to do if you're in a very small constrained device. Someone else has worked out the problem of how the crypto actually works itself. And you may get benefits of things like side channel attack protection, where someone may be trying to look at the leakage of information in a device. As was said this morning, right? Don't define your own crypto standard. Don't just use XOR. Okay, you might not get XOR wrong, but it's not actually going to give you any protection. So focus on existing standards that work, but make sure their devices, their standards that are have some road ahead of them, and they're not already deprecated or about to be deprecated, or just generally going to be broken. So you have to define a secure architecture for the device that you're building, and there's you can provide a whole list. And one of the things the work of the IOTSF is about is well, what is best practice for these types of things. So how do you manage keys? Have you done things like inhibited debug on your device, or have you left the debug port open? You need to base your security on the keys and that you're using, not on just obfuscation, because obfuscation just it can be broken by people working hard enough at that obfuscation mechanisms. Imagine what the attacker has total knowledge of the whole system, but they don't have the key. What does that entail? What does that entitle them to do? If you've kept your keys or your root keys safe, but the rest of the system is known to the attacker, what does that allow them to do? Is there still mechanisms where they can exploit the system, or do they actually need that key to go make things happen? Maybe another example, we've seen numerous times where some of the crypto systems we have are reliant on being able to use random number generators, use random numbers for keys, etc. Many times there's been examples where there isn't actually enough entropy in the system, so the random numbers aren't actually random, or they can be derived, or they can be worked out. So you can figure out that the random numbers, the key that's being used is not a random key for a session. It's based on time of day when the key was generated, for instance, or something like that. So you need to ensure that you've got sufficient entropy. If you're using random numbers, they really are random. Integrity of devices. It's all very well trying to have some confidentiality in your system, but it is reliant on there being some integrity in the platform. So we've seen embedded systems in the past, typical microcontroller type solutions. They're usually very isolated type devices with narrow levels of connectivity. And the big change with IoT is about making devices that are naturally widely connected and building complex systems from these small end devices. So you need to be able to provide a verifiable root of trust inside things like edge nodes. So things like being able to have strong cryptographic identifiers in the devices, whether it's a unique ID for device, a unique key for the device, and the mechanism to derive and store keys in a way that's isolated from the rest of the system. One of the other mechanisms that is regularly used is being able to provide hardware isolation mechanisms. So having extensive memory partitioning in the device or code execution spaces in the device which are isolated from each other. And a typical example of that is used for doing things like a secure boot foundation for trusted software, so that as the device boots up, it is checking the integrity of the next piece of code that is running on the device, so that you know at the start of day only trusted software is installed and executed on the device, and you have a mechanism which allows for a quick method of software authentication. So yeah, we're firmly of the belief that if you build something, someone's going to have a go at attacking it. And what's happening is, the capability of attackers evolves very rapidly. If there's some information that someone has, now it becomes very freely available. Number of types of systems exploding, and the values of attacks potentially growing as well. And you have to envisage that they're not just, it's a snapshot attack. It might be taking place over a long time. It might be taking place very persistently across a whole range of devices in the system. And again, you have to, from a system perspective, you have to think about which parts of the networks are trusted or not trusted. Can you rely on employees not spilling secrets that they have about how things work? You can't. Just being able to go, well, I built this design, and when I built it, these were the potential threats that we thought about. These were the potential vulnerabilities. Those are the things we've done. That's the blacklist of known compromises. That's no longer sufficient. So in terms of how do you support availability of on devices, then yeah, absolutely, isolation of system components. You have mechanisms that allow you to isolate flaws, vulnerabilities that are found. Does that actually make your system simpler to test and validate if you can break it down into smaller pieces? And that's always a challenge between, do I have smaller pieces which I can manage in themselves, but then I've got the communication mechanisms that I have to handle between devices, or is it better to have a larger blob where I don't have the communication, but it's a much larger blob to handle? So the other issues you may want to consider is real-time monitoring in your system. Do you need real-time monitoring of what's happening? Is there some method you can do for analysis of what's going on in the system? So cryptographic measurements of status. As I said, you can do that at boot time as you come up. What happens after the device is booted? There are mechanisms you need to use to check the status of the device. And then finally, recovery and remediation. So is there a mechanism which allows you to isolate certain pieces of the system and replace compromised components in those? How do you manage to update the system over its entire life cycle? So we've seen a lot of work happen in the mobile phone space. I have a lot of background there. And a lot of that type of technology could move directly over into things like gateway applications. But the edge devices, if you're going to more and more constrained microcontroller, IoT, microcontroller-based devices, they need to catch up in a lot of these areas. So things like extending the traditional MPU model for memory protection units, being able to separate application and critical functions on these low-level devices. Do you need watchdog mechanisms to monitor system resources? As I've said, adding secure boot onto devices to allow correct code installation and structured recovery capabilities. You know, what's the mechanism you do? As you say, is there a kill switch on the device because it's cheaper to have a kill switch? So then, what's the control mechanism on a kill switch? You know, do you want someone to just come around and go, well, I'll just turn off all these devices and kill them? Is there a mechanism for update on the device? Can you manage that in a secure way? Again, if you're adding a mechanism for update on a device, then you're also adding a potential threat there. Someone could reuse that update mechanism to go and attack your device. So when we're going through the steps with some of the people we're dealing with, we usually work in this kind of flow, which is understanding what are the threats that are involved in this particular system, in this particular design. So what are the core assets that we're dealing with? And the assets might be very different for different types of system. There's such a variety. What's the value of those assets as well? And again, the value isn't always necessarily obvious. If you can use a very cheap device which has been compromised to provide a more general attack, then the value of that attack may not be what you think it is. So from the one before about the turning on the valves for the water or turning on the hose, well, if you can turn on every hose in the city, right, what's the difference between knowing that and turning on the valve at the water station? So understanding what the potential attack vectors are, bearing in mind that there's going to be new ones coming along that you can't even dream about. But also, what are the consequences of an attack? And yeah, balancing that security measures that you need to implement and the cost that will entail versus the risk that something will happen or the cost of a breach. Use those to feed into system definition. How do you define the secure architecture? What are the hardware and software pieces you need, usually down at edge devices? Does that fit in with the things like your power and area budget as well as your cost budget? What's your definition for system robustness? Do you need to worry about tampering of devices or not? Sometimes, you know, if it's a device in the home, you know, you can say, well, why would the user be interested in tampering with their own washing machine, right? They might be interested in tampering with it to find information about other people's washing machines, but why would they tamper it with themselves? But you know, we've seen so many times that yeah, maybe they do actually want to tamper with it. That moves on then to architectural implementation. What does that mean in terms of the system IP, the system design? If you're building a chip or a device down there, how does that fit in with the chip design that you need to do? And then what's the auditing or certification process you need to go through, whether it's a self-certification or just a design audit? or whether it's through one of the formal certification processes as well, penetration testing and how that rolls out into the market. So requirements for next generation security. Yeah, we need some real defense capability against cyber threats. So more interesting features in the edge device, in the edge devices and constrained devices that you're going to be using. That's definitely coming. People need to make sure they use them. Look at all of the integrity, confidentiality, and availability. And yeah, don't let the attackers win. Okay, thank you very much.